Hallo? Okay. Dames. Er is mij gevraagd, oh yeah, it's in English I think, no? If possible, that's possible I think. So I will speak English. So, first of all I would like very briefly to introduce myself. I'm Wim Parijs. I work for Janssen, the pharmaceutical company of Johnson & Johnson. I'm the head of a group that is called Global Public Health, R&D. So what we do there is we look in a very dedicated way, very specifically, at addressing medical need with solutions, be it new drugs, be it technologies that can assist delivering solutions for medical need in resource-limited settings. It all started with TB. We also have HIV as a main topic. And we just finished 2 phase 3 studies with a long-acting antiretroviral therapy. And we hope that with injection every month and maybe even every 2 months, that study is still ongoing, we can control viral load, so treat HIV, which of course would be a tremendous innovation. So HIV is what we're talking about today. We also have a dengue project, and I was here, I don't know how long ago, Serge. 2 years?
Exactly, 26th of November.
Wow. 2 years ago, for a dengue hackathon. And we're here today for the HIV one. Why are we so interested in HIV? We have the products, and we've been working on HIV treatment for a long time in the Janssen organization. We brought 3 antiretrovirals to patients. But there is one big problem, and of course you've already had a lot of introduction to it and worked on it for a long time, I've heard. So a big problem is when people fail their treatment, we have to understand early, as fast as possible, that viral load has gone up again, and most of the time it's due to selection of resistant mutants in the virological pool, or the virus pool. So we need to understand that, because that triggers an intervention. You need to put patients on new therapy that works against that mutant resistant virus. If you don't do that, you continue the treatment. As we said before, there is an opportunity cost, because somebody is taking medication that somebody else could take, and that is not working because the virus is resistant against it. The other thing is a patient being treated with treatment that doesn't work anymore, nobody benefits. And we have to make sure that we change that therapy to something that still works on the virus. You can go out and do viral load testing and resistance testing everywhere, but that's, first of all, extremely expensive. And it's also a very difficult thing to do, because these tests are not readily available in all resource-limited settings. So we were trying to find another way to predict where the problem with resistance occurs, and then you can have targeted diagnostics or targeted interventions. So that was the whole idea on how can we get at that predictive model where the most resistant viruses occur. So that's why you are all here and have been working on it for a long time, and I really want to thank you for it. Spending your time on this is actually very much appreciated. And I'm looking forward to the presentations and to the outcome of your hard work. So that's about it for me. At first, no, I have to hear how I did. What were the 3 criteria?
5-4, 5-3, 5-7. Excellent, thank you very much.
Does it work?
Yep.
Okay. Okay, so here we are at the end of almost 36 hours, 36 hours. And we started yesterday around noontime, 1 o'clock, with a lot of folks coming in, high aspirations. And throughout the day, we discovered new ideas in support of HIV, in support of HIV resistance. And there were quite actually very inspiring things, new things that within a company, we tend to think out of the box, but sometimes we're too prudent. We like to continue to hold the box while we step out of the box. And this session, this 36 hours, is precisely to get further away from the box by inviting you all, by calling for data, by calling for your talent and your inspiration, and bringing new ideas. We started off, I think, with rather 15 teams, and more or less 10 teams survived, continued working until today. And I can tell that there are some inspiring thoughts, some new thoughts in there. And so here we are, ready to kind of hear the pitches. But before and then go into the jury or the judging. But before we do that, I'd like to say already now that all of us, all of you, are already winners. Throughout these 2 days, we've had opportunities to talk. We have opportunities to help each other on pitching the ideas, on focusing on some of your key strengths of your presentations. So in the end, everybody is a winner here to start with. So that's my 2 words. Where is he now? Voilà. These are my 2 words. Philippe, is that good? Because then I hand it over to you, Master of Ceremony. And you are ready to go and call the first group on stage.
That's right.
Sorry, yes. Thank you. So here we are. This is team 6. So we have Michel, that he had to leave, Heaven, myself, Maria, Nevidita, and Hans, and Lars, which was not in the picture, basically. So sorry. So, okay. So the project is about the prediction of, to create a predictive model for, so for actually HIV viral road actually risk in and predicting its behavior in terms of seasonalities and areas in geographical areas. So then, so this would be crucial in terms of allocation of resources and also on interventional and so in intervention of for political makers in terms of addressing this disease and it's in the specific for HIV progression and transmission. So how we are going to do this? And so what is well known is definitely is seasonality and how it changed during the periods during the year, and then how it changed during the around the areas in Africa, and then we will focus on the specific for Kenya. And what is also known is that there is a strong relationship between HIV progression and transmission with some other variables like meteorological variables, like malnutrition around the the countries and the area itself. And those are well known also to have sort of seasonalities. So why don't explore and then see whether there is any correlation between those seasonalities, and then that can help us to understand so how so where be ready and go and intervene in go in intervention for HIV diffusion. So first step, of course, is finding the data, and then the reason. So the main important thing is that those other variables like agricultural variables, meteorological variables, or other variables, those are more available. They are more easy to obtain with respect, of course, to HIV data or test data, which we managed also to find some. So that's that we are sort of proud of. And so just to go quickly in the data details. So we found virus load tests at the country level, monthly based. And also another data set based on with subpopulations, so divided by gender, age subgroups. And so for meteorological, we had rainfall based from satellite images, and agriculture, where we used prices for maize and dry beans, of course. So we are still considering, and then we will, that will be part of the project, to also evaluate whether the choice of those variables are actually drivers for agricultural and malnourishment in the country. So the crucial part is the development of the model, and then I will switch with Hans.
Does this work? Yes. All right. So thank you very much, Maria. So yeah, the models that we were thinking of course, focused on all the data. So the subpopulation data was also very important here, played a big role in helping to predict the viral load suppression in each county or even sub-county. So what we did is actually we did a very extensive modeling procedure. So we started with a generalized linear model. We added some tree-based models on top. Then we did some gradient boosting models. And well, we also added some deep learning models. But the final result is actually the combinations of all these models, which will result in the most generalizing model. And I think if we look at the final estimation error, it's 6.2% in accuracy. So what we tried to predict was how many, or what the suppression percentage was. So suppression percentage here is determined by a viral load that is below a certain percentage. And so we tried to estimate the percentage of the population that falls below that percentage, that falls below that threshold. So threshold was 1,000, which according to the Kenyan data set resulted in suppression of HIV. So we tried to predict this percentage level at county level, and so the final model had a root mean square error of 6.2%, which is actually quite good. The way this was validated is by both cross-validation as well as a test data set which was unseen by any of the models during the training. So all right, so a bit deeper into the models. So what did we learn from the models? Well, very important things, of course. The historical data that we have from the counties based on these viral load suppression rates, of course, are very important in determining the viral load suppression rates for the next month and the month after that. But what actually caught us by surprise is that, for instance, rain from the weather data, as Maria mentioned, can also have a really big impact. And that sort of surprised us. But apparently we see several reasons as to why that could happen. What else did we see? Well, if we went through the data and we looked at these subpopulations, we also noticed that if we looked at the male and the female groups separated, we noticed that there was actually a relatively high correlation coefficient between the male and females. And more specifically, if we looked at the males at the current time, and we used that to correlate it to the female suppressant percentage in the next month, we could actually see that there was almost a 35% correlation, which is, it's not that significantly high, but it makes you wonder whether or not you can use the subpopulation indicators as early risk indicators for other subpopulations as well. All right. That's what I wanted to say. Besides, oh no, we have a few insights. Of course, the summary, and I will leave that to you.
No time for insights.
No time for it.
If you go to our final slide, you can explore our interactive dashboard where you can see how this data changes month by month over a 3-year span. You can investigate it by county, and you can also see our prediction for January 1st of 2018, which was not captured by the data we looked at. Thank you.
Any questions?
Yeah, maybe I'm not sure whether you have touched the point that how you deploy your approach to the real ground. How do you deploy your solution to the country?
So what you have with our model is a fairly good prediction within the year for the cycles of high and low risk times. But of course, that doesn't take into account actual data of drug resistance and is simply a predictive model. So the next step would be to gather this data over the next 2 years. So continue to validate the periods of risk according to the indicators. And then especially validating the model by sending out people to test actual drug resistance at the times of year when our model predicts that it would be higher or lower in order to see if the model is right. From there, it would be relatively simple, as everything is, to allocate resources and plan ahead for the higher and lower risk seasons, region by region.
It's a hard job, but I will try.
Ready?
Yeah.
Whenever you're ready, you go.
So
Take your time. It's okay.
oopsie, my presentation is somewhere there. So sorry. Where is my presentation?
So your presentation is already on the board, huh? Your presentation is already
Yeah, yeah. Let it be. I will try to just see through and back. And okay. So hello everyone. My name is Varun, and this is Lucas. And another team member of us, she has to leave early, so yeah. Let's go into our problem to deal with the problem which we are trying to solve. So for us, we saw this this problem of Kenya, and we are trying to solve the problem of virological strains which have more likelihood of occurrence in Kenya. So what we are trying to incorporate in our situation is how these because these are like, they are different strains level which are being in each of these virologic drug resistance, for the drug resistance, we have these virological strains, which are quite heavily important in each of the tests which people, which doctors take for suggesting for a patient if they are having drug resistance or not. And then there are different mutations which is happening at the same time. So we are trying to first we will try to go through the situation in from the Stanford database, which we have collected the data from the Stanford database, which has all these drug resistance data available there, and we will try to quickly go through the EDA of that, and after doing the analysis, we will try to explain what inference or what model we are trying to use in terms of getting the likelihood of each of those virologic strains happening in specifically for Kenya. So, and what impact this can have it on the people living in Kenya. So this particular solution we are trying to deploy, we would like to deploy for the specifically for not just for the doctors, also for the organization. They can merge, they can actually come together, and once they have this likelihood of all these strains happening, and then they can quickly understand what is going on, how these different levels of drugs, these resistance is increasing. And so the data set information is we have like 4,000 plus unique observation for each of those patients, and they have been drug resistant. They have been tested for drug resistant, and they have each of those observations. We have the mutations which are happening for those patients. And what assumptions we started with is like if a patient is having a resistance towards for any of those mutations, if it is greater than any single major or minor mutation, then definitely that patient is going to be drug resistant. And if the patient tested is not having any of those mutations, any of the major or minor mutation, that person is not having major and not drug resistant. I mean, yeah, he's not drug resistant. Yeah. And this is the population density. So I have taken this from Steve from the ResearchGate website. And this is the mapping of Kenya, giving the correct locations of the places from where we got the data from. So if you quickly see that this is the place where the highest density of population are living, in the center, in the south, in the north, and we see that we have only data from Nairobi and mostly in the south and the north side of the region. So if just taking a specific, talking about the specific region, we see that we have the viral strain from this data set. We saw that there are 46 patients for NNRTI mutations. So these were the mutations happening for that specific region. And this is something which we are going to infer on for the whole data set. So this if you see, this is a whole observation data set in which we have collected, and we saw that these are the different levels of percentage in which all these mutations are happening. So and just querying on the network, we see that inhibitase for all these 4 different types of mutations which is happening, we have these different levels of patients, and who are drug resistant, who are not drug resistant. And if you see distribution of this strain for each of those, I'm only talking about the database which we collected and we scraped through, and then just try to collect try to make information on it. And the Bayesian modeling which we have tried to implement on it is, sorry. I would like. So the model which we actually try to infer upon, the first posterior of the first baseline which we have got from this 4,000 plus observation, is that we turn out that this group is particularly the inhibitor, one of those groups in which the higher likelihood of happening of this on the log odds ratio. So and plotting it on the distribution plot, we see that these log odds has the highest distribution in inhibitase as compared to RT and PR, although we have more information. And then and just to confirm it, that then we also saw that there were increased cases of I&I resistance. So here I will just finish my talk, and yeah, thank you so much.
So, are there any questions from the jury, please? No questions from the jury? No, the boys are here as well.
Just one
It's fine.
quick question.
Can you put back your microphone?
I just want to. Can you maybe just repeat once more how, let's say, compare your contribution or how you see what you did with respect to what was existing before, and maybe make a difference between we see some existing research and what you did.
So from the existing research, after going through a lot of research research papers on about these drug resistance, people, all these doctors are giving away their, they are talking about their information on these particular sample of people they have tested, and then they are reporting the drug resistance mutation which is happening on those patients. So while going through those and then understanding the how they are actually inferring on it, because they take this sample out and then they try to stretch it to a big population. So this is, but when I tried to look up on a lot of Googling, I did a lot of Googling and find out there was no information on actually any baseline of this drug resistance in country. So when I saw this inhibitase specific resistance happening, and I confirmed it with this just in 2017, this market report that there were 4,000 plus inhibitase related drugs were deployed in the market, then I saw that there is a connection between the specific drugs which are being deployed because of the resistance happening.
Maybe I can give some final closing words, because this is a very exciting project, and Varun is very deep, obviously, in the matrix, as you can see, working on a very complex model. But what he's basically trying to give is help those people who take decisions as to where, at what point in time, we need what sort of medication to be able to take a better decision, even if there's not much data available. So this is where he does the Bayesian inference. And that way we hope that in the future there is going to be a foregone, obviously, opportunity costs when allocating medicine. Yeah. So does that sum it up a little bit?
Worked for more than 2 months on this project, so he is very excited about it, as you could see.
Test.
Your clicker is here.
Okay. Okay. Good afternoon. I represent in Team 3, Kionibot. Let's get into context telling the story of Adam. Adam went to a funeral that ended up in an orgy. As you may know, this is one of the traditions in Homa Bay in Kenya. Then she's a bit concerned if maybe she acquired HIV. So her friend is asking, and she said, "Did you do the test?" And she replies, "Well, yeah, you know, I went to the health facility, I walked there for 5 hours. Then when I was there, I had to wait for 3 hours, and I really wanted to go to the toilet. But the toilet was a mess, so I went out of the facility and I went to McDonald's. And after doing my business, I saw the face of Ronald McDonald, and I heard him saying to me, 'Don't worry, you don't have HIV.' So this sort of conversation can give us detailed patient-level information that can be very useful for validating our models. And this is what if there can be a technology that can mimic a conversation and can provide a questionnaire of questions and answers. This is what a chatbot does. I'm introducing you a solution for HIV data collection, KioniBot. A bot is cheaper than surveys and provides us new and accurate data to validate and create new models. What is the need that we are solving for the user? Kioni offers an optimal and a map that can tell the user the optimal health facilities that matches the illness to treat or test. Because as we know, not all hospitals treat all illnesses. Is this important? Well, just remember how much friction to go to a health facility Adama struggled. And on the other side, we're talking about data. This is not even registered in Google Maps. Our value proposition is a win-win situation where we ease the user the friction to go to health facilities and many other variables. And on the other side, we collect the data that we want and in the format that we want it. This bot is a powerful technology that is manageable according to the stakeholders or the key players involved. And also according to the models we want to validate or create. I see a bot like a piece in a big puzzle of the HIV data collection and data modeling. In this conversation journey, we want to create an interactive, friendly relation. This means that if we start by providing a service like a health location, after a year, we can be the friendly reminder to take the medicine. Kioni in action. These are 2 screenshots of Kioni. It's already working on Facebook. Something happened. Philip, excuse me. Okay, sorry. And you can see how through an interactive, friendly interface, we can provide information of the map location. The conceptual architecture, there's a mismatch between what is shown here and what is shown there. This is sabotage. This is sabotage. So, let's all face there. So, this is their conceptual architecture. So we have our chatbot with the defined rules, and then and afterwards we have an R interface that it's talking to the data set of Congo and to the Google API. Then the chatbot collects the information and sends us to creates a new data set and sends us to the stakeholders. And then we close the loop. We focused in this hackathon using the data set of the Republic of Congo, and these are our results. You can see how the map of the health centers of the country is different than when we filtered for the ones that treat the HIV treatment. And also you can see here a result of the Kinshasa city and the number of HIV patients. So it tells you if a hospital is more crowded or not. And in this way, we can reduce the waiting time. That is a big issue here. I want to say thanks to the team because this could only be possible through an interdisciplinary effort. And also, thank you very much to all of you, and especially the boot campers, Digitizer, Johnson & Johnson, etc. Please, questions.
Yeah, so I was wondering, so I assume the purpose is to roll this out in a certain country. What is your strategy going to be to get people to use this chatbot?
Okay, so we can go to the, who is also clicking there? Philip, sorry. Okay, okay. Because I could go back to a slide, but as you can see in the list of stakeholders, there are different people working on this. So for example, Mom Connect is a service already provided by Johnson & Johnson that you send text messages to pregnant women about, and then you reduce the risk of HIV. Another one is a survey running in Kenya called Kemfia. So you will have, please, I know I have a baby. You will have different strategies according to with whom you are working with. The idea always is that we know that this is a new technology, so we should have a guide that tell you, look, this is a bot, this is how you use it. It's like the first time you used Facebook, or the first time you used Gmail, or the internet. But after you are in, it's a different story. So for sure, we need an onboard strategy. We can be hospitals, can be NGOs, can be any of these projects running on, and etc.
Excellent. Any more questions? Do you have a question?
Any more questions?
Excellent, well done.
Thank you very much.
C'est très important. Mais il faut que vous soyez tous les deux là. Yeah. Hi everyone, I'm Ludovic, and here is Ricardo, and here is Lucas. Very important to remember their name to understand what is going on in this presentation. Oh yeah, and these are our face 1 hour ago, so there is a reason for that. Okay, the two challenges that we try to address in this project are one related to the data collection and data quality. We want more data, and we want data aggregated by months and by districts. And the second challenge we try to address is the stigmatization problem. So someone doesn't take his drug because of stigmatization, is ashamed about talking about what happened to him. So we try to address that as well. And the solution we find is building a reward system, an incentive system to empower local communities. So the vision, the pillar of the approach is locals know better. And you will see what we mean. So I really ask you to focus on these 6 elements of our solution, otherwise you will be lost afterwards. So the first one is the local partner. So in our example, it will be Lucas. Local partner is a local partner of the project, of the pilot project that we are building, and health provider. And the second one is me. I have the HIV, but I take my drugs, so I don't have more problem about that. And the third actor is Ricardo. He has HIV, but doesn't take his drug. And the 3 other elements, our reward system, which is mainly a network, a database, and another database which contains the test results. When someone is having a test, all the results goes in that database. And the last element is the web application we built for the project. So how these elements interact. Here are the 3 actors, Ricardo, me, and Lucas. The goal of the interaction is to bring Ricardo, the red man, to Lucas, to the medical center. I know Lucas, who works at the medical center, and he tells me about this project. So he brings me to the medical center, and I will follow a training on the web application. The training allows me to enter in the reward system. What is my task? My task, now that I'm trained, is to find Ricardo and to sympathize with him, because I also have HIV. I want to bring him to the health facility, and the pillar is really well placed. And Ricardo and I, we will go to the medical facility, and Ricardo will have his test. Once he has his test, we both check in the web application. We do a double check-in. The double check-in triggers the data flow, so the data of the test goes in the blue database. It also triggers the reward flow. It means that in the database, we will be rewarded by this action. Let's talk about the web application. The web application does does three things. So the education, I was educated through this application. It provides a marketplace where we all can spend our points that we have earned through this reward system. What is in the marketplace can be discussed later. And it allows us to do the double check-in. Here is a mock-up about the web application that we built, but we don't really have time to go through that. Yes. And here are the phases of the project, how we see it long-term. So the phase that I just talked about is 2019, is the pilot. And I will go quickly to that. What happens if the project grows? If we have more than 2 partners, then the database grows and become a liability, because it is storing value. So it could be the target of some hacking. So the solution we propose is to build a blockchain system around that to secure the database. And that's it.
Any questions from the judge, or is it that clear?
So the question is how they do find me and how they bring me to the health facility. The thing is, probably if someone made the first test, so this is in the hypothesis of someone already made the first test and then never came back to the health facility because of the stigma, because of many reasons. So the idea is to try to scan lots of facilities and have them to share data about people that came in for the first test and then never came back. It's one way that we could aggregate some people that we know that they are HIV positive, but then we never heard about them anymore. This is one case. But then there would be, we would have to develop many other hypotheses to work with locals to then aggregate those people that might be also concerned by this same situation, but perhaps they never made even the first test. So that's another segment. And probably we would have to invent many other ways to find all the people and to gather all the people concerned.
Just in one sentence, the locals knows better. That's the idea of working on a pilot project. It's to go on to find 2 partners and ask them how they would do it. We bring an architecture of a system. We don't bring all the solutions. But very good question.
Thank you very much. Who's the talker? You're the talker. Yeah, you'll get the microphone then. You're more to do that, huh? But it's just a bit complex. The clicker is there. Okay.
I don't know. Okay. All right. Good. So the clicker. All right. Good night, everybody. Good evening, everybody. We're Los Pollos Hermanos. Our team name might ring a bell to some people. It's known for drugs, but drugs in a different way. They also look at drugs in a supply chain, from a supply chain perspective, and we also took the same angle to the problem. So we started from this use case where you have a patient which is HIV positive, and it takes them too long to reach the medical facilities. Actually, the medical centers, they don't have any visibility on the supply or the demand, and they just hope that the medicine arrives to the patient. So actually, the core driver for this is the fragmented and inefficient supply chain. And if you look at it from two perspectives, you have the costly black box with a lot of middlemen, a lot of chaos. And at the end, you don't have the demand management. You don't know where your demand is. You don't know where you have to ship your products. So what we came up with is to capture data in real time using IoT. And we built this, that's why I brought it here on stage, this little Raspberry Pi Zero, which is actually capable of sending location data, temperature, and humidity data about the environment. And this can actually be attached to a set of packages of medicine so that it can be tracked through space and time, basically. And this allows you to do things like this. So this is a demo visualization which we built, which my dear friend here built in Splunk, which allows you to in real time see where your packages are at, how they're moving, and to see where the stock places are and stuff. So our solution architecture looks like this. So on the one hand, we have at the moment the Raspberry Pi sensor, which is a proof of concept, which dumps the data via REST API into MongoDB, which is a NoSQL database, and then we have a data visualization happening in Splunk. Actually, what are the benefits to this? So skipping the technical pieces for this, it's actually the full traceability and transparency at last, actually, because we've had a lot of workshops. We've been seeing teams that are having trouble finding the data. This actually provides you with the sensors that you need to capture the data, to identify flows of drugs, map stock locations, to identify early possible shortages, and to identify areas with low availability. This is also an enabler for optimization, so it kits out the middleman, locates the bottlenecks in the supply chain. Also for the future, it's a database for future applications, so once you've gathered a lot of data, it allows you to, with AI, with machine learning, and this is something that some people among us here know better than I do, allows you to build all kinds of predictive models, very, very cool applications. Also, it helps you to closely follow up on the conditions of your drugs. So it helps to in early detection of bad drugs due to circumstances, as there's a temperature and a humidity sensor on here. And actually, to roll this out on the local level, there's not a lot of dependency on the locals, which is a great, something that we've had as a feedback here when we were pitching our idea to the coaches, is that a minimal reliance on local teams is the way to go. Is if we can control it from here on out, from our side, then we can actually control it better. So this is a slide that we found in our research, is that shows that 151 million vaccines actually are getting lost to improper refrigerating, and this is outside of the HIV problem. Within HIV, we've heard that HIV medication is actually more resistant to circumstantial factors. But it can also be applied to other pharmaceuticals, so that's why we put it in here. So there are also some challenges to have this. So there's some financial viability. Financial model needs to be worked out to see how much sensors we need to attach to which parcels, to maybe pallets, to trucks. That needs to be found out. Also, the connectivity of IoT, maybe it's not everywhere we can connect to it. There might be fraud, and also about patient privacy. This is also one of the issues that need to be tackled. So this is it, but we have one more thing, which we worked on. We also covered the last mile. So not only until the stock places, we also built an app, Skylar, which might also sound familiar to some people who watched the series Breaking Bad, which is a proof of concept from a mobile app or as an MS service that is complementary to IoT sensors. So our IoT goes until the medical centers, and from the medical centers onwards, the Skylar app takes over. Skylar app is actually a bit like Deliveroo, where a patient can request medication, and these requests are mapped on a map, and then a supplier or a rider can find it. And our app developer here, Charles, he's going to give you a little overview of a demo. So this is the supply solution architecture where it neatly fits into the IoT thing that we had, also via the REST API. It's putting it to the database. So just to have a little a demo.
Here is Skylar. So you can either join as a requester, so you're going to be a patient that requests medicines, or you can join as a driver, and then you're probably going to deliver medicines to patients. Here are some screens. So you can, when you join in as a requester, you have a map showing the facilities nearby that have some stocks in the medicine that you would like to get. And then you can get some more information on the current stocks and then place an order, just very much like it's done in Deliveroo and other apps like that. And then once the order is confirmed, you'll get a notification once the delivery guy wants to deliver the order to you. And for the other side of the app, for the drivers, then it's very much the same thing, but in the opposite way. So you have a map showing the orders to take up in the area, and then whenever you feel like you want to help someone, you take up the order and you deliver it to the patient. Now, I have a note to say, this is a mobile app, but we're going to have interfaces with SMS so that people that have kind of an older phone can still use our core features.
All right, this is it. Thank you so much for your attention. Thanks to the coaches and the people organizing here. We were Los Pues Hermanos.
Thank you so much for taking the time to put this together. Mine is just a little bit of a clarification. You mentioned you wanted as minimal local involvement as possible. What do you feel that will have in terms of sustainability of this particular intervention in a local community?
Yeah, it's a very good question, because attaching sensor and just sending it out to the local community is something that is not sustainable. You cannot just keep on sending sensors. So we've looked into this, but it's something that still needs to be worked out. We were thinking about a resending option, so people, when they arrive, they can send it back with the postage is already paid, but this is something that needs to be worked out. Very good points.
Excellent, well done.
Test? Okay. Yeah, I see. Okay. Yeah. Hi, we are Team Artwork. We will maybe explain the name of the team later on. So we started with this picture that was found by Samir to remind ourselves of what we were here for, actually. So if you look at Africa and healthcare, then we are actually faced with a medical system in disarray, and people go to traditional healers, or they self-medicate. And so what we were thinking of is doing something structurally. Oh, there's something wrong with the slides. Yeah, okay. So, but yeah, so what if we look at what is already in place? We have the World Health Organization, and in order to fight drug
resistance, they've come up with guidelines for treatment. And we see that these guidelines are implemented by national governments. Now, so they can provide, you can provide adaptation best practices all you want, but if they're not being followed up, then you have a big problem. So in the national guidelines database that is online, we see that the guidelines that have been collected so far date back to 2005 and 2011. So that's almost 7 or 8 years ago. So currently, what we see is that in the workflow, you have the World Health Organization guidelines, then you have, well, best practices, and then you have the national guidelines. The problem is here that as soon as something gets fixed in, sorry, it's my wife. So as soon as something gets locked in legislation, it's stuck over there, and it's very difficult to change all that. And more importantly, whenever something is stuck in there, and the guidelines are fixed, then this affects the people that take their medication immensely. So what is missing, according to us, is a monitoring system. So if you have guidelines and you want to implement them in national governments, the problem is that they're committed, but you can have all the adaptation best practices that you want. If you do not follow up on them, you can have in the long term mismatches which will render your anti-drug resistance policies ineffective. So what we want to do is we want to work on the policy level to have maximum impact. And so what we propose is that we have some monitoring of the guidelines that are being implemented in the national government. So what you want to do is you want to have a guideline and have a system in place that warns you whenever something is outdated or whenever there are discrepancies. So what we want to do is we start from the guidelines that are present in the WHO documents, and then we want to inventorize everything which is available in national gazettes, national consolidated legislation, and also in the preparatory parliamentary work that is being done and is recorded in the parliamentary proceedings. So yeah, again, you should see normally a screenshot here of an application where you, as if you're a public servant, what you want to do, what you want to see is you want, of course, first of all, you want to know that something is lacking in your legislation. And if you run a query on that, you want to know that something is missing. So what we want to do is we want to build this application for the following people. So we want to work on the policy making level, and we want to make sure that the people that are there, so the World Health Organization people that are in legislation and people that are involved in healthcare policy making have the instrument to follow up on these guidelines. And also the people working in NGOs, because eventually they'll be affecting the strategy. So how do we want to do this? We consider this, or we will frame this as a traditional text mining problem. And there we discern the haystack and the needle. In the haystack, what we will be doing there, and we've done that during the last 2 days, we are going to reconstruct the national documents. So they're out there in the wild in the form of scanned documents, so they're not machine readable. And so what we will be doing, sorry? Okay, so and how we will do this, we will use modern state-of-the-art embedding spaces techniques, and then there is this last how we want to do this. We believe that the software that is going to put there, that it is best suited for grassroots development. If we can convince people at a local level to use it by making it as accessible as possible, then we believe that it stands a chance of growing a community. In terms of sustainability and deployment, the system as we see it will allow for added value services. For example, it's if we are scraping all and inventorizing all of the legal data, you can imagine that this is useful for legal practitioners, and they could co-fund the upkeeping of the infrastructure. That's it. Thank you. Questions? Yeah.
Just one question. How do you relate this with HIV drug resistance?
Okay, that's a good one. Yeah, sorry, I forgot to mention that. So we believe that this is a concerted effort. So if you want to ensure that everyone is on the same page, is following the same guidelines, then you stand a better chance of preventing drug resistance. And to do that, in Europe, we would come up with a interoperability system so everyone is on the same page. But in Africa, that's unfortunately not the case. And what we want to do is we want to make sure that all the guidelines are being aligned. And currently, we're working with the things that we have. So we collect all the data and we just mine it. And the idea is to notify people in time. Okay.
This. Let's go.
Hello.
So, it's up to you, man.
Okay. Good evening, everybody. My name is Kevin Albert. I represent this team. This team is called Stock Out. We spreken bijna allemaal Nederlands. We vonden dat op zich grappig vergeleken met de leeftijdscategorie dat hier rondloopt. So, let's continue in English. I presented a pitch that was oriented towards finding the need of drugs projected onto a visualization, and then on top of that, the availability of drugs. Sounds easy, but then if we are charged with the idea of thinking out of the box, we were more hitting against the box, me at least. So at some point, these young people were interested to join us, and we started to build like 2 groups. And the idea was to make a solution that is ready for implementation. Therefore, we have a group that was focused on the backend, the data preparation, and then a group that was working on the visualization. So, next slide. I don't know the problem. Identify shortage location of HIV drugs, right? So, as I mentioned, hitting our head against the box, yes. We were trying to get the right data. The Tanzania data was nice, and we tried to clean it and present it for them. So next slide. Yeah,
Maybe yes. Thank you, Kevin. So as Kevin already mentioned, we trying to tackle the gap between the demand and the suppliers of HIV drugs. So the stakeholders, we are going to work very locally on national level. So you see all partners, we have to co-work together to collect the data, to co-work to also find the doctors and pharmacy to can distribute those medicines, drugs of HIV. We need also co-workers by policymakers and authorities to have on the we can also work on the legal way. Maybe we can also go to the next slide. Well, so that was the problem. So after a problem, you need also a solution, and the solution is, as says, mapping and visualize the regions with the shortage of HV drugs in Tanzania. And after a solution, then will come a conclusion. Indicating the short problems, problem with an interactive mapping tool. I see some face expression, show me the expressing tool. So we will not show it, we will demonstrate it. So please, can we demonstrate the mapping tool? So after it will comes. This mapping tool should be the fundamental base where all the projects can build on it. So we hope after this project hackathon, the other groups will work further on their project. They can use our fantastic interactive tool. So as you can see, the interactive tool, it's all in Tableau. It's very accessible. We can implement it on a web page, very mobile friendly. So there's no problem about accessible or something. So it can work in Tanzania, if I'm realistic. So I will start by the first first mapping tool. You say the shortage a year of HV drugs. So by starting 2013, there were a shortage of 11,000 shortages of drugs. In Tanzania, you see also the map of Tanzania over there. So there will give you by population how many shortages there are per population. Then you have also the facility per population is also very important in the things we are doing. The facilities, the health facilities. So in the everything's okay. Okay. So in the blues, the blue regions are the better regions compare other regions in Tanzania self. So and then we can also by the tool map. We can mapping by located all the facilities. So this tool can use in a reality way. We can implement it directly in on a web page, on a mobile device, if we can co-work with those partners by our stakeholders. And yes, thank you for your attention, and yeah, best luck.
Question from the ladies, from the berries.
So, who is the typical user of this dashboard, and what do they do with it?
Firstly, the data scientists, they will have to collect
local ones.
Of the national level, yes, because we have to collect the right data, and the data are it's located on the national level, and also by NGOs. Most of partners they are active in those countries has also a lot of knowledge about this data. So they are also one of the main users of this tool. Some other questions? Okay, thank you for your.
The next team is also the youngest team of this hackathon. Their statistical average age is 17 years and 22 days.
Okay, so hi everybody. We are Team Super Dry. We're not sponsored. So we worked during the weekend on the project of improving the Tanzania data sets given by Serge at the beginning of the hackathon. So first of all, our goals. So we had three major goals. The first one being to clean the, oh yeah, right, I forgot. Wait, how does this work? Okay, so the first goal being to clean the existing data. So for example, if one value seemed too low or too high and wasn't really at its place, we had to try and correct it for it to be right. Then second goal was to predict the unknown values, because as we can see, there are many missing values. And so one of the big goals that we had was to try and predict these values. And our third goal was to use all of these to try to modelize the different interactions between these data. Okay, so we divided our project into 3 different phases. So the first phase being what we called the exploration phase. So what we did during this phase was delve into the data set, try and find what we could do with it, the different types of data that were available, and try to understand already certain relationships between the data, as well as start plotting a couple of graphs. So this is one of the first graphs that we plotted. The second phase was what we called the correlation phase. So this is the phase where we decided to merge different data indexes in order to try and find relationships between different datas. So trying to see, for example, if 2 different types of data were, sorry, I can't find the word. Yeah, currently, but I mean, never mind, okay. If they were, for example, mathematically linked, which could then help us modelize a function, which will help us later for the modelizing of the rest of the data. So modeling was our third phase. Oh, wait, never mind, okay. So by using linear regression and polynomial regression, we tried to predict the missing data. So for example, the graph on the top right, the blue, dark blue bars represent the data that was given to us, and the light blue bars represent the data that we predicted using regression. And then the 2 graphs at the bottom are just to show that we think our algorithm works pretty well, because the one on the right represents the population with the data that was given, and the regression line that was created, we put it back here, but with the new values that we created, and they correspond, so we're pretty good. So the way our algorithm works is that it's going to go through the whole data set, and every time it finds a unknown value, a data gap, it's going to try to see if it can predict its value, and if it can, it'll just go to the next one, and it'll repeat this process until most of the data missing has been created. So to finalize, this project is really important for data scientists, but also researchers, because data is something that's sometimes really difficult to get, and with such projects, we really think that we could help development, a better development of knowledge on HIV drug resistance. And we also think that if such algorithms had been used before, the projects that were made this afternoon could have been even better than what they already were. So, thank you.
Questions from you guys?
So I have a question. Are you the eldest of the family?
Yeah.
So what do the youngsters do?
No, they don't. They're not into data science. I can try to form them.
Excellent. Congratulations. You've impressed us very much.
Thank you.
Thank you.
Go on stage, find the clicker. These youngsters, you never know.
Hello everyone. Good evening, fellow hackers, members of the jury. We are NLP, or Now Let's Proceed, and that comes from natural language processing, because that's what we are going to do. And in this talk, we will talk about three things, basically the problem, the solution, and we will end with a quick overview of what we did. And the problem is fairly simple. It's finding information. And it's not just finding information, because that's quite easy, but finding information that is relevant, that is reliable, and that is structured. Because in this day and age, we're loaded with information, and health care information data is 85% unstructured data, exactly. And what we would like to do, or what would be nice, if that there is a system in place that can provide you the data in a structured way, also based upon who you are. Because if you're a health researcher or a local health worker and you're looking for information, or if you're someone else who has who is infected with HIV, you're looking for different information. And that is what we're trying to solve. So we came up with a web application that structures this data, and on top of which we build a recommender system so that the information that is retrieved by the system is personalized, relevant, and structured.
And in order to do the structuring of the documents, we have decided to use a natural language processing that feeds the topics, the structured data, to a recommender engine, which afterwards is being used by the user interface. What is nice with this system, and why it's important for HIV, is that if we prevent people from getting drug resistance, then we can save them. If we give them the information that they are missing, then we can save them. And in here, we can see that in this particular example, we have trained a model for researchers. We have trained a model in order to be able to show the main topics that we have in our documents, which are available in English, because the model can be trained in all the languages. And also, the application, it's easy. Only 4 steps, and you have the information. You log in, then if you want, you put a search word. You can see the different profiles for which we have thought about training the application. Here you see, okay, you are logged and you are searching for art, and then you have the recommendation. It's easy, it's fast, it's scalable, it gives the pertinent information for the persons. It can be directly put on the cloud, so everybody can profit. It can be used in collaboration, in sharing by different stakeholders. We are covering just a small part of the forest that can become a playground for this application. The system is learning by itself, it's autonomous, it provides relevant and valuable information for the people which are most in need for that information.
Any questions? Yes.
I was just wondering how you filter the information that will become available, because there's a lot written, there's a lot known. So if an individual has a certain search term, which because if you would go thousands of
yes,
findings.
Thank you for the question, because that's a really interesting question. In fact, Google only does ranking-based search. We are providing 3 types, in fact 4 types of algorithms. We are providing collaborative user search, we are providing content-based search, ranking-based search, and keyword search. And that means the application, based on how you interact with it, it will change, it will evolve. And also what's really nice is that based on the way people interact with it, somebody in behind can see, but in fact people are searching rather this term, and this term. So maybe we should concentrate on that, because people need that particular information. And what's also really interesting is that you don't have to be local. You don't have to be there in order to help people. You don't have to be on site in order to provide the insights that people need to get their treatments, to know what this disease is about. Because we are speaking about stigma. If people have to go to a facility center in order to have the information, maybe they won't do it. But if they can search that online, at home, and we have seen that, for example, in Kenya, 85% of the people have internet connection. And if somebody is informed, then we think they will react way better.
More questions?
What are your data sources behind this?
We have trained a model for now just on the research article in English. But the application itself has a part in which you can state the language that you're going to feed in the documents, the profile for which you want to fill in the document, to feed the documents, and also that it's really simple. You just create a folder, you give a name, you put the documents, and you say, make me the training for English, make me the training from French. And then it will automatically detect the language of the document, and it will only select the documents in that particular language to do the training. And what we can do as a further implementation for the application is to do automatic translation of the topics that have been already detected, automatic translation of the documents which are being fed in, so we can offer the same information with the same relevance in different languages.
Just a question to make sure I completely understand your concept. Who do you think will benefit more using this application? At which level do you think it will have the most impact?
All stakeholders.
Oh.
The answer is quite easy.
Yeah.
Because people can learn about their disease. They can learn what can happen if they don't take the treatment. Researchers can learn what are the other papers that already exist on a particular subject. Because what's also really interesting in the application is that it shows the topics that exist with the words that exist already. So when somebody is searching, he can say, ah, okay, but in fact this is also linked to this, it's also linked to this, which makes that information that maybe he didn't even thought about is gonna pop up. And also in the recommendation itself, based on the profile of the person and the similarity with other users, we're gonna recommend articles that he didn't even search, because we start knowing the person. And by knowing the person, knowing the articles that he's reading and what he's liking, we can propose other subjects. And maybe he will decide not to read them, but at least he will be conscious about the fact that those articles exist also.
And just to throw some more light on your question, so why we decided to come up with something that it's not only going to help HIV drug resistance, but for other diseases. If we look at the situation of Ebola in Liberia, some community health workers got infected because they lacked rapid relevant information. And we think with tools like this, not only applied in the case of HIV drug resistance, it could prevent such situations in the future.
That is why we have said we have just covered one tree, but we have the complete forest for which you can directly deploy the application.
Well done. Thank you very much.
Thank you. And just one thing, thank you for this hackathon, because it's really nice.
Yep, it's there. Good evening, everyone. If there's one thing we've learned in the last 2 days working around HIV resistance, it's that actual data is very limited. So we are Team Explore Data, at least part of Team Explore Data. And I will first present one of the solutions to this problem, and then my colleague Jellert will take over and explain the second solution we have found for this issue. So it's common with drug resistance research is that we work with proxies of drug resistance, because as I mentioned, the actual data is missing. And these proxies can be the percentage of viral load non-supported, non-suppressed, and the number of people that are on second-line drugs. So our idea was to enrich these data, specifically for Tanzania, using data we have scraped from open source data information, including factors such as social demographic, health facilities, and also road infrastructure, and to see if these data can complement the information we have on HIV parameters. So the method we have used is a hierarchical clustering of different regions using these enriched data of only non-HIV parameters, and then see if we can find a relationship with the actual HIV parameters. So the result is shown here on a map. We've been able to cluster 3 regions with an underlying factor analysis of population density, the amount of investment, and also the level of development of the different regions. And then on top of that, we have mapped the viral load non-suppressed, which is a proxy for drug resistance. And what we can see is that we can start to find a trend with the different regions, especially with the population density and the development with this proxy. I need to emphasize that we have only used the most reliable data, because what we have found in the data source is that if we look at the outliers of these HIV proxies, is that removing these outliers based on the source information tells a different story. So based on the most reliable data, we have shown here that we can, to conclude, use these types of analysis to sit around the table with stakeholders, including the government and also non-profit organizations, to determine action points specific to each region, targets with specific policies, and also campaigns. So talking about action points, Jelle will take over and show an actual actionable solution to a second problem.
All right, so the second thing that we did is a text mining exercise. And I won't go into much of detail right now because I'm going to try to give a live demo. But before we're going into that, one of the things that we did is build a topic detection model. And I just want to show you how we've done that. So there's 4 topics, and the algorithm gives us back some words, doesn't give us topics. So we came up with topics ourselves using our own business knowledge. So the words that came back for the first topics are, for example, treatment, patients, resistance, ART. So we said, well, that's all about resistance to treatments. The second one is about again, treatment, but very specific. You also have milligrams, days, hours, tablets. So we said that's really clinical treatment information. And then the third one is about population, more linked to education. As you can see, there's education involved in that circle. And the last one is population combined with geography, because we have words like region and district and stuff like that. So let me go to my laptop. Mag ik even?
Ja, natuurlijk. He's the last one, so if he breaks it, it's his problem.
Thanks. No? Almost, yep. Fair enough. We'll go over 5 minutes, I'm sorry. Already? Okay, sorry. So, our model. So this is our GUI. And, well, there's nothing much to do. We can only press one button, so I'm going to load a PDF. It's in data. I'm going to select a new one because I'm not going to select the PDF on which we've trained our model. So I'm selecting PDF, one of these. So I'll pick this one. Okay, now this button is available. It says text mining. So okay, let's execute the text mining. It's basically as simple as that. Not responding, wow. Okay, so now it says topic detection. Topic detected, and the topic is resistance to treatment. Let's go to the output now. So, text mining, output. There's a lot of information that is being saved. So here, this is the PDF that I've selected. And as you can see, you get the 4 topics and the probability that this document belongs to those topics. So sometimes you have 60-40 as well, stuff like that. What do we also get? We get a bar chart with the count of the most occurring words. And again, you see resistance, ART, drug, treatment. So that's proof that it actually belongs to that particular topic. And you get a word cloud as well, but it basically gives the same information. So what do we also get is the images from that PDF file. And you get all images, so you also get this kind of images. So that's not very useful, but you also get the useful images, these kind of graphs. And then let's click the last button. That's the CSV downloader. So it will now parse the PDF file. Let's go to that same PDF file so we can compare. Which one was it? This one. Okay, so this is the PDF file. It's still running. And you'll see that in the output, you have an extra folder created now, tables, still parsing, and now a CSV file should appear. There it is. And it contains the data from our PDF file. So as you can see here, that this is one of the images that was extracted, and it was extracted multiple times, once for each page. Here we encounter our table. Can everybody read it? Yeah. So we have our table, but as you can see, it's not perfect yet. You have your data, but this column should have been split further. So it's not perfect yet, but at least you have some data and you can start building models. And then here in our PDF, there's proof that it actually extracted the graphs. So this way, you as a researcher, if you receive a PDF file, you can quickly run it through this code and get a quick overview of what it is about, and if you're interested in reading it, and if you're interested, you can extract data and then again start building models. Some next steps is, as the previous team mentioned, build a recommender system, but also build models on this. And
excellent. Thank you very much. Hold on, maybe there are questions from the ladies of the jury. This concludes the presentations of the people of the finalists, basically the people who managed to go to the finals. It's like doing a marathon. It's getting to at the arrival, being there. That's when you are a winner. We had 12 winning teams here, and they all deserve a very warm applause. So the next step is the most difficult part, and this is the part that all the participants will not have to take care of. This is done by us. It's to select the nominees. In the meantime, I would like to invite you to some excellent Syrian food that has been cooked here nearby in a Syrian restaurant, and some Italian food that has been cooked in another local restaurant. Everything is being served upstairs, so you need to take the stairs. Give us 1 hour to select the nominees, and come back here at 11. We'll be calling you whenever we are ready. Thank you very much.